Here's another example problem that we can apply the law of conservation of energy. So a block with a mass of 3 kilograms rests against a compressed spring. The spring has a stiffness of 147 newtons per meter, and the spring has been compressed 70 centimeters from its natural length. So when released, the block flies off the edge of the desk with some velocity that's yet to be determined, and therefore follows a half parabolic trajectory. So we're asked, how far away does the block land? What's the range of the projectile? And also, what's the speed of impact? So the block is going to impact the ground at some unknown angle, and that total final speed is something we have to solve for. Okay, shouldn't be too difficult. So let's do this. Let's figure out what we'll call this V initial. How's that? And then this is V final. So to get this initial speed, we should label a point A in the diagram that represents the initial state. And in this case, in that state, there's some stored potential energy in the spring. When it gets to position B, then all of that potential energy has been unleashed and converted into kinetic energy. Of course, at point C, there's an even greater amount of kinetic energy due to the loss of gravitational potential energy as it falls from a height of 122.5 centimeters. Anyhow, let's just study for now the conversion of energy from point A to point B. If we know how fast the object flies off the edge of the desk and we know how tall it is, then we should be able to use that to figure out the range. Okay. So from point A to point B, mechanical energy is conserved. Now we could write out this full long version of the equation for the law of conservation of energy. Initial kinetic energy plus initial gravitational potential energy plus any initial elastic potential energy has to equal final kinetic energy plus final potential energy plus final elastic potential energy. It might be a bit excessive to write out that full version of the equation. It's probably better just to look at your labeled points and say, what are all of the forms of mechanical energy here? Well, in comparing from point A to point B, there's no change in elevation. So we can, for now, let the reference level h equals 0 at this upper surface. So there's really no initial or final gravitational potential energy to account for. Really, all we have at point A is the energy stored in the spring, 1/2 kx squared. When it gets to point B, then all of that energy is lost and it's developed some kinetic energy. So there's elastic potential energy at point A that's been converted into kinetic energy at point B. So here we have 1/2 mv squared. So those have to be equal based on the law of conservation of energy. So we can cancel out the 1/2, and V then would be equal to, let's do a little algebra, divide both sides of the equation by m, take the square root of both sides of the equation. Oh yeah, V would be the square root of k over m multiplied by x. Okay, so the value of x is 70 centimeters, k is 147 newtons per meter, m is 3 kilograms, so this means our velocity is the square root of 147 over 3. Now let's be clear on the units. This is newtons per meter per kilogram. Oh boy, a newton is a kilogram meter per second squared. We're dividing that by meters and also by kilograms. Kilograms cancel. Right. Interesting. Meters cancel, yeah. We get 1 over second squared. If we take the square root of that, we get seconds. Well, yeah, but then we're going to multiply that times 0.7 meters. So we get 1 over seconds multiplied by meters to give us meters per second as a final result. Okay, well, do the number crunching. 147 divided by 3 is 49, and the square root of that is 7. So V is 7 inverse seconds multiplied by 0.7 meters, which gives us 4.9 meters per second. That's how fast it's flying horizontally off the edge. Okay, now to find out how far away it lands, all we have to do is recognize that horizontal and vertical motion are independent of one another. So the horizontal distance is the initial horizontal speed multiplied by time plus 1/2 the horizontal acceleration times time squared. Now there is a vertical acceleration of 9.8 meters per second squared as it falls to the ground, but there is no horizontal acceleration. So this whole term goes to 0, and this is just the dirt equation. Oops, I'm sorry, this is not Vx, this is x. You probably caught that already. So to get the value of x, or it's just as well to call it capital R for the range, we just need to multiply 4.9 meters per second, the result we had from conservation of energy from A to B, multiplied by some amount of time. Well, you should know by now that the time of flight is just equal to the square root of 2h over g. So this is the square root of 2 times 1.225 divided by 9.8. Grab a calculator, see what you get. Yeah, this comes out to be 0.5 seconds. Okay, so the range is equal to 2.45 meters. So we've answered our first question. Now the second question, what's the speed of impact? We're going to try this two ways. One, the old familiar way, we're just going to use kinematics. And then the second way, we'll try the law of conservation of energy. Okay, so for the kinematics, we just have to recognize that this speed of 4.9 meters per second horizontally never goes away. And then it's influenced by this vertical component of gravity for a time of 1/2 of a second. In other words, the final vertical speed is the initial vertical speed plus vertical acceleration times time. Now there's an initial speed of 4.9 meters per second as it flies off the ledge, but that's applied only in the horizontal direction. The initial vertical component to the speed is 0. So the final vertical speed at impact is 9.8 meters per second squared times 0.5 seconds, which gives us 4.9 meters per second. Oh, I'm getting the idea that this thing must be impacting the ground at a 45-degree angle, right? Flies through the air in this half parabolic trajectory. It has a horizontal speed of 4.9 meters per second, and its vertical speed has gone from 0, and it's gotten larger and larger until when it ultimately hits the ground, the vertical speed is 4.9 meters per second. Well, when the two components are equal, then that implies an angle of 45 degrees. Although the question wasn't asking what's the angle of impact, it's asking what's the total speed of impact. So the total speed can be found based on Pythagorean theorem. Take the vertical speed squared plus, the horizontal speed squared plus the vertical speed squared. Add them together, take the square root, or I think you can reason this out that this is going to be the square root of 2 times either Vx or Vy. So this is rad 2 times 4.9. Which gives us about 6.93 meters per second. Okay, well, if we get the same result based on the law of conservation of energy, then hopefully you develop greater faith in the law of conservation of energy. So let's see how we can go about that. So we have the block compressed against the spring. That's point A in the problem. Then we have the block as it just starts to fly off the edge of the desk. That's point B. And then it strikes the ground. And that's our point C. So the energy at A should equal the energy at point B, should equal the energy at point C. We can actually cut out the middleman here. We don't have to calculate the energy at every point. Ultimately, the total energy at A equals the total energy at C. I'm going to change my reference for this case and say H equals 0 all the way at the ground. Okay, so based on that, we have to think, what forms of mechanical energy exist in state A? Well, the spring is compressed, so there's some elastic potential energy, but at point A, it's also up above our reference height. So there's also some gravitational potential energy, but the block is at rest in position A, so there's no kinetic energy. Now, at point C, all that energy in the spring has been released, and the object is back at our reference level. So all we have now is an object impacting the ground with some kinetic energy. Okay, so we get 1/2 kx squared plus mgh equals 1/2 mv squared. And we're trying to solve for this speed at impact. So probably best we multiply the equation through by 2 and divide by m. So we get v squared is equal to kx squared over m plus 2gh. Double check the algebra on that one. Looks right. So the final velocity is the square root of k over m times x squared plus 2gh. Numerically speaking, this is 147 over 3 times 0.7 squared plus 2 times 9.8 times 1.225. All right, let's take it piece by piece. 2 times 9.8 times 1.225 gives us 24.01. 147 divided by 3 multiplied by 0.7 squared also gives us 24.01. So our speed is the square root of 48.02, which, no surprise, gives us 6.93, assuming we've got the units right, meters per second. Hey, look at that. The law of conservation of energy gave us the same result. And notice along the way something conceptually that we've learned. We don't have to account for the energy at every step along the way. We can always just compare the very initial with the very final in coming up with the result we're after. All right, thanks for watching.